Looks like we're just about there. Welcome back, everyone, so far. And it's official. We can now start our third week of the semester. Welcome back, folks. I do have several announcements I want to discuss before we get started with today's work. But let's turn over to the class first. Any questions, comments, concerns, or anything to start us out with today? Okay, well, let's run through those announcements. As far as what we have going on so far, our first quiz that's been posted, quiz 1, is going to be due next class. And by the time we are back on next class, I'll have quiz 2 posted. It'll be at the bottom of this week right here with the due date of the next Thursday. So pretty much the cycle you're going to see here with the quizzes, the lecture notes, the readings are just going to cycle through as we go from week by week by week. But new things do happen on this week. We've crossed the last day to add or drop full semester classes. So the class roster is a little bit more solidified. And so because of that, and it being week 3, this is a good time where I'm going to, in the weekend, contact every student individually to determine your preferred location, your preferred campus for taking the exam. I'm going to assume that if you've registered for the section 02, this is the folks in class right here physically today, that you're probably going to take the exam in class. So I'll just contact you just to confirm that. And I'm going to assume if you're in section 22, you're probably going to be taking the exam at the Pocatello Testing Center. If a different testing center works best, then just let me know. But that's what I'll be working on towards probably either Thursday or Friday, just getting that information. Then as far as the exam is going to go, let's scroll down to about here. Because we're on week 3 and exam 1 way down here is on week 5, that means this is the point at which I start getting going with including more materials down here. I'll say the exact coverage on a section by section basis and include a bunch of documents for purpose of reviewing for the first upcoming exam. And more critically, let me go back to the syllabus to remind myself. One element about this course's exam is that, let's see here, it's closed book and closed notes. So we have to be ready to go with certain formulas. I do attach a formula sheet at the back of all the exams. And so I want to get that document ready to go as soon as possible once we get closer to the weekend. I'm going to post that formula sheet right here, right at the top above calculators allowed for the exams. And that way, once you see that document, you'll know what formulas are included on the exam, what formulas we're expected to have memorized and ready to go with. So I'll try to make that document really apparent right here. So when you're studying, you'll know those materials. Well, that's my major announcements for the day. Any questions about the exam or the upcoming material or otherwise?
When is our first exam?
Oh, good question, actually. There's a couple spots you can check. On the syllabus, we've got the exam slated for, hang on. I just noticed a problem with syllabus. That should say Tuesday and Thursday. Let me make a quick note to myself. There is most of my classes are Monday and Wednesday. I think that's how this happened. It's going to be Tuesday, February 11th, but let me just get a reminder going here. This is a good one for all caps. I should say something like fix the day by day schedule. Really glad you asked that question. That's alerted me to a big typo here. I think the bigger problem is this class usually ran on a Monday, Wednesday. It's now kind of a change of a pattern, Tuesday, Thursday. And the other way you can find the exam date more reliably until I get that revision posted is just right here. So it'll be Tuesday of this week, so February 11th. Any questions about that so far? Okay, again, for the folks that are more near this campus, I'll assume that you're taking the exam in person. If the Idaho Falls Testing Center works best for any particular reason, even if you're in the online section, if the Idaho Falls Testing Center is better, I'll make that exam work out with that testing center or the Pocatello Testing Center. And pretty much how it works for either testing center is I have to send that testing center a roster of the student names, the exact time of the exam, all that kind of stuff, the actual exam. Once they get all that information, they ask me to contact you again so that you can call them and schedule a time to take the exam. So it can be any time on Tuesday, and that would be perfectly fine. Well, that's probably all of my announcements so far, unless I forgot something small. Other questions or comments so far? Okay, well, let's jump into the material so far. It looks like for exam one, it's probably going to be sections 2.2 through section 2.5, but we'll see where we end up with on the end of this week. And where we left off on section 2.3 was right here, the very last question. We didn't want to rush through this one because it's an implied question, but this is just a good way for us to say, after we've done all this hard work on limits, say the prior problem up here, dealing with graphs, single side limits, limits that give infinities as outputs, it's good to just put this down as a concrete problem that anchors all this mathematical material down. So here's the context. It says, a patient receives 150 milligram injection of a drug every 4 hours. So let's take a look at the graph and see if it really says that. At the time 0 hours, we go up to 150. That looks like it's the milligrams. Let's say here, on this axis, this is the milligrams of the drug. I noticed something odd about this graph already. Right here, highlighted in yellow temporarily, this is at time 0 hours. So this is assuming this was what was the first injection. Patient was supposed to receive 150 milligrams, yet there's an open circle right there. I think that's a good idea to just address this right away. Anyone see what that open circle is conveying really? Kind of strange in a way, right? Because it says we're supposed to get 150 milligrams at time equals 0 hours, but that open circle says 150 milligrams isn't actually obtained, not by this graph. We put a solid dot right here, we would say, yes, we got right up to exactly 150 milligrams. So what's going on here? Why is it an open circle? Well, there's two ways to answer that kind of question. One way to answer it is, this is a mathematical model for the drug presence in the blood. And no mathematical model is perfect. It's just our best approximation of reality. They put an open circle here, possibly just to convey that right at that time, we didn't get exactly 150 milligrams. Maybe there's like a microgram or something of the drug left in the syringe, something like that. We just know we went right up to just below that amount. So that's what that graph is trying to convey by putting an open circle there. Does that make sense so far with what's going on with the graph? Awesome. We're also told this patient receives the drug injection every 4 hours. Who knows what this drug is? That seems concerning to me because it looks like the concentration is just going up. We start here at just about 150 milligrams. Then as that drug is metabolized in your body, it drops down to whatever this level is. But that's the 4 hour mark. We have a new injection and now we're up to whatever this value is. Then there's a small metabolizing washout period, new injection, and it gets even higher. And the graph just continues in this way. Hopefully we're not killing the patient. We're just trying to get up to medicinal and it'll start to taper off. But this is the picture so far. It says next, the graph shows the amount F of T. This is the portions of the curve in red of the drug in the bloodstream after T hours. So altogether, this is one graph, even though it's in 6 different segments, or that would be 5 different segments if I count that right. All we're doing in this problem, now that we have the mathematical model, is taking a look at 2 limits, and the harder thing, giving a practical interpretation for each one of them using the context. So let's give these a try. Starting off with this one, we're taking the limit as T heads towards 12. T, because we're thinking of time, but it has a single-sided direction. We're at 12 hours coming in from the left. Let's use the little trick of working on a note card. So imagine you printed out the notes, you have a note card available with you. This is that note card. Oh, what in the world did he do? It's not supposed to minimize anything. Don't know how that happens, but anyways, going back to this, when this says we're heading towards 12-hour mark coming in from the left, it means we place the note card about right here. We don't care about any information towards the right. We're just wanting to know what is the value of this limit. I forgot to put in f of t to make the whole limit statement more grammatical. And now we're on our way. The limit as we head towards 12 hours coming in strictly from the left is following this curve down. And it looks like it's getting closer and closer to about 150 milligrams. So we'll place 150 milligrams there for that first limit. Does that make sense to folks on how we found that limit there? Okay, we still have to give an interpretation towards it. I'll do that right down below, but at least we've got one limit down. Let's try this one here. Limit. It says t heads towards 12. The plus sign we read as heads towards 12 from the right-hand direction coming in of f of t. Because of the direction here with the plus, we would put the note card on this side now, meaning we don't care about what's happening in this direction. I also need to make sure we can see the axis. There we go. So heading towards 12 from the right. Any volunteers for what the value should be?
300.
Good call, folks. Looks like we're going to be coming up this direction, outputting 300. Absolutely. So 300 down below right here gives us 300 milligrams. So we've got it, folks. We have the two limits down. Now we have to do the actual trickier part, in my opinion, of saying, what do these limits mean? But honestly, for the interpretation, you can just kind of read this out. Just recall what F was meant to be. F of T is the amount of the drug after T hours. T is 12 hours here, but the directionality is also important. We came towards 12 hours coming in from the left, so we need to convey that in our interpretation. So let's say as we get closer to the 12-hour injection, because we're thinking of time, and I'm saying we're getting close to the 12-hour mark, that's conveying we're at about 11 hours, 45 minutes or something like that, getting closer and closer to 12 hours. So usually when you're saying I'm getting closer to a value when it's time, you mean coming in from the left-hand side, because we can't time travel at the 13-hour mark and go backwards in this kind of configuration. So we'll say, as we get closer and closer to the 12-hour injection, the presence of this drug in the bloodstream gets closer and closer to 150 milligrams. Checking the graph, that's what's happening here. We're getting closer and closer to the 12-hour mark, and it's dropping lower and lower to 150 milligrams. So let's say, as we get closer and closer to the 12-hour injection, the presence of the drug drops off towards that 150 milligram value. So that'd be my way of saying this one right here. There's lots of ways you can convey this kind of limit, but to me, that's what seems to make the most sense. Does that look all right to folks? Any words you would include or exclude out of here on that statement? Okay, well, let's try it again. This one's different because it says we're coming in towards the 12-hour mark, but from the right. But again, we can't time travel, so we're not saying as we are time traveling backwards. We just want to say right after the 12-hour mark, we are about the height of 300, so 300 milligrams. So let's say for this one, if you're coming in towards a time value, but from the right, we can now just say just before, or excuse me, just after the 12-hour injection, the concentration is, I would like to say just after the 12-hour injection, the concentration is 300, but there's an open circle there. So we have to say just below that 300 value mark. So we'll say is just below 300 milligrams. So again, these are kind of tricky problems because I think everyone feels comfortable getting the limit out, reading it off the graph. But we have to say what the limit means. It's a little bit trickier because there's lots happening on these limits. There's directionalities going towards them. But actually, I think what makes this problem the hardest is this part right here. We had to say the context as we gave our answer. So we had to say something along the lines of there's an injection happening, there's a presence of a drug, and we're dealing with units all at the same time. So those kinds of elements had to be in our expression when we went to describe the limit. Not saying if you left off the word drug, the whole thing's suddenly wrong. You just have to make sure you're saying something about the original context down below here. If you tie it in even just a little bit, I would consider that a full answer. But that's our application problem that goes along with these limit problems so far. Any questions at all, folks, getting through this one?
Hi,
Okay.
sorry, I had one question.
I'll go ahead. Yeah.
So when looking at like the limit for t to 12 negative, you said it was 150 milligrams. Is that because before you inject it's at 150, but when you're looking at t to 12 plus, it is after you inject, so that makes it 300?
Yeah, that's exactly right. So just
Okay.
before we're at the 150, but then just after it jumps up to just below 300. Exactly
Okay.
right.
Perfect, thank you.
Yep, absolutely. Other questions so far? Okay, well, let's save up these notes then. We usually don't finish a section this fast, but we had just this one last hanging problem after we came back from the weekend. Next section we're going to look into is really just this stuff all over again, except the major difference is the graphs are missing. We still want to evaluate the limits, and so we'll see how to do that algebraically next. So let me close this first. We always get like a little bit of a mental break before the next notes come in. Here's finally those next notes. And it starts off with something, again, kind of familiar, like we hinted at before. We have limit laws coming up all of a sudden, just like before. Really, the only major difference between these limit laws is in section 2.2, we were taking limits as x goes to either negative infinity or positive infinity. So every one of these directionalities, x tends towards a, were replaced with x tends towards infinity, with the understanding it could have been a positive infinity or a negative infinity. But the same exact limit laws get duplicated again. Now for dealing with these kinds of limits, when you're heading towards a finite number a, so a there could be like a 5, 7, negative 2 million, something like that. There's a lot of limit laws here, so just like in that other section 2.2, our goal is not to memorize every single one of these in the list, but just become familiar enough so that we know how to use them. I am just planning on including one of these lists as the last part of the formula sheet on exam 1, just to emphasize our goal isn't to try and memorize them verbatim, just be familiar. But taking a look at these, we have just a couple remarks before we get started. We're looking at one of the major parts on the very next section of calculus. Calculus is divided into 3 components. Continuity, that's a statement about limits, and we're getting really, really close because when you take, say, these limits right here, say limit law 10, all we did is we replaced x with a. We just plugged it in. Turns out that's a property of continuity, directly substituting in a value. So once we get through learning and understanding these limit laws, we'll be getting into continuity. We hinted at differentiability. You can see the notes at the very top in section 2.2, where it's all about. It's about slopes in essence. And integrability, this is about areas under a curve. So it's kind of nice in a way that we're about to do one of the 3 cornerstones of calculus. And the other reminder in these remarks is that it says here that the limits below both exist. In fact, if one of the limits fails to exist, maybe it's this one, limit x tends towards a of g of x, then we did this right here, the whole thing doesn't exist. So if one part of the limit fails to exist, the whole expression is ruined. Let's write that out just to be specific what we're saying. We'll say if the limit as x tends towards 3, let's say for g of x, does not exist. That was our shorthand from the last section notes, or you could just say undefined. Then the limit as x tends towards 3 of f of x plus g of x also does not exist. Deserves an exclamation mark, because another thing that's a little bit tricky here is whenever we do a limit and we get an infinity on an output, that's also a limit that doesn't exist. We have to give the infinities on our answer because we're giving more information. That's the way the limit failed to exist. But if this one, say, was equal to infinity, for example, now this limit doesn't exist, and the one below also wouldn't exist. It could possibly be infinity, negative infinity, or no value that we could put here whatsoever, depending on what the function f of x does. But those are things that we have to watch out for when we look at these limit laws here. They will break down if there's a problem with one function or the other. They have to give us finite numbers, in other words. So we'll practice these limit laws in a couple ways. First, I know we've looked at graphs a lot, but first we'll see them through the graphs just to see how they go together. Then we'll be very shortly after that applying them to these kinds of examples, where it's just a random function. We have to calculate the limit of each of these weird things we see here. So last part of the notes is kind of our major objective of this section. And above is how we're going to get there, first with these laws. Any questions at all, folks, before we begin working with them? Okay, let's give this a try then. So my first example is just seeing this done through a graph. It says here for the instructions, graphs of functions f and g are given. So f of x is on the left, g of x is on the right, and just playing with the zoom here. We're going to use them to evaluate all the limits. And if the limit doesn't exist, we have to explain why. Also, it says here, the limit law is used to cite that law. That's not something I'm going to ask you to do on quizzes or exams. That's more for the sake of the notes. So we see how all these limit laws come together in this problem. So these are the limit laws that are up there in the notes. Here's the first problem of the day. Limit is x tends towards 2 of f of x plus g of x. Looking at this situation, at 2, we have an open circle for f of x. That's okay. That's not going to break the limit. Let's look at the g of x graph. At 2, everything is connected, so that's even a nicer limit. It looks like both limits exist. And so we just use this property. As we take the limit as x tends towards 2, we just break up the limits into two statements, a cross addition. So here's our first step on this one. This is equal to limit as x tends towards 2 of f of x plus the limit as x tends towards 2 of g of x. We are citing the limit laws, again, just for the sake of us getting used to this document right here above in the notes. And we use limit law 1. So I'll just abbreviate that to LL1 as written here on the document. So this is by limit law 1. But once we use limit law 1, we're home free. We've done these limits before in section 2.3. If we go to 2 on the function for f of x, this is a double direction limit. So as we come in from the left, the height of the curve is getting closer and closer to a -1. And it's doing the same as we head towards 2 from the right. We get a -1 overall on that limit. How about for the 1 on g of x? Anyone spot what the value should be for this limit? Good call. This one would be exactly 2. The way we kind of look at this is we first look at this part, x is heading towards 2. So that means we're in this region of the graph around 2. Then as we come in from the left, it gets closer and closer to a height of 2 up here. Similarly, as we come in from the right, we're approaching that height of 2. All this finally tells us the limit itself is a positive 2. Last step is nice, and we just do the ordinary arithmetic. Now it says if you add these functions together, this function plus that function, take the limit as you go towards 2, you just get a value of 1 on that limit. Well, that's 1 down, 5 more to go, but any questions, folks, on the first one? Okay, next one, let's do it in the same kind of way. We have limit as x tends towards 0 of f of x minus g of x. If we'd be using a limit law, that would be limit law 2. Basically the same as the one above, we're just changing the sign to a negative from a positive to get a negative out here from the positive. But before we actually crank the limit out, we should do what we did over here as well. The mathematical idea is look before you leap, basically. We're taking a limit as x tends towards 0. We're in this region for the f function, this region for the g function. For f, no problems. It's a connected graph right around here. The limit would be 2. But for g, this is different. It looks like it depends on the directionality. If you come in from the left, it's up to 3. But if you came in from the right, the limit is a 1. So what would you say the best overall answer is for this one? Good call. So there's a big problem with the g function. The graph itself is disconnected. We'll later call this discontinuous. And a break like that with a double-sided limit gives us does not exist. We have to do the tedious thing of saying, if it does not exist, explain why. So we'll do that next. Oh, and sorry for the person who wrote the chat, forgot to write that down. So we've got it does not exist on this limit right here. And for the explanation, it's all about what happened to g of x. We'll say it does not exist because the limit, as you tend towards 0 for the g of x function, let's say if we went toward the left, heading to 0 toward the left would give us a value all the way up to 3. And the limit, as x tends towards 0 from the right of g of x, is equal to, well, this one is dropping down to a height of 1. So limit as x tends towards 0 of g of x, that's now a double-sided limit, does not exist. So there's just one problem with the original limit expression. The g of x function doesn't have a limit as we tends towards 0. So that means the whole thing is a does not exist on this problem. Well, any questions, folks, with that one there? Okay.
Couldn't you just use the closed circle for the g of x?
Oh, good question. So the closed circle here for g of x, this part right here, would correspond to that limit right there. As we head towards 0 from the left, we would get, oh, sorry, my note card is acting a little weird. So if we did the 0 from the left, yeah, you would have the value of 3 in this direction. But the trouble with g of x is, if you change it and go this direction, now we have to use the open circle direction. That's when we're heading towards 0 coming in from the right over here. It drops down to a 1. So if it was a limit statement written out this way, limit as x tends towards 0 of g of x, but you're coming in strictly for the left, you would absolutely use this value right here, like you mentioned. You would get the -3 on that one. Or excuse me, that's a +3 on that one. Let me just put a plus sign on that. That's a value right here we're highlighting in yellow. But the reason that one there, where 0 doesn't have a plus or a minus, it's now the double-sided limit, doesn't exist. It's because we went up to a solid dot for a limit of 3. We went up to the lower dot for a limit of 1. If those values are different, we get a does not exist on it.
Yeah, I thought
wait.
because it would be an open circle, it's just like theoretical, so.
You mean this open circle right here?
Right. Like,
Yeah, we
I would
would
get it if they were both closed circles, but
Well, the trouble with both closed circles is if they were both closed, say like that, then this graph would fail the vertical line test because a vertical line would intersect here and here as well. So we wouldn't be looking at the limit of a function any longer. But even if they were both open circle, we would still have the same kind of limits. And let's see if we can maybe look at this from another direction. If you took a look at, say, trying to change my pen out, sorry about that. We took the limit as we head towards 0 of g of x, and we had a value of 3. The only way that would actually work is if we took, and let me change my highlighter here. We would have to take this part of the curve, bring it up here, and make it go like this. So in other words, this whole portion right here, let me see if I can white it out. That's a little tricky. This is going to be like a nuke, but that'll do the job. Let's just imagine there was nothing there, just normal grid lines. If the curve looks like this, then everything is fantastic. We get now to say the limit as x tends towards 0 of g of x is absolutely 3. And even if we blew a hole right here, I mean, it's kind of rude, but we are blowing a hole right. Let me try again. Putting a hole right in the graph at this spot. There we go. Even if the graph looks like this, with the open circle right here, we could put a solid dot right down below. The limit as we head towards 0 of this function g of x would still be 3 because we're heading towards 3 on the right. On the left, it's getting higher and higher towards 3 on the left now. And this limit would still exist. Even with the solid dot again defined way down here, it would just mean that g at 0 is 1. But the limit as you head towards 0 is getting closer and closer to 3 on this now highly modified graph. Does that make sense with the question about the values here, Eddie?
yeah, it does. I didn't, with the limits kind of confused me.
Yeah, me too. They're definitely tricky, especially when there's weird directionalities wrapped up with them at the same time. So thanks for asking about this concept here. It's really slippery concept in my opinion. Other questions at the moment?
I have one.
Yes.
So for the f of x, does that mean that for the limit on that one would be 2, positive 2?
As we
Or
head
because
toward,
it doesn't have a point, it wouldn't be 2.
well, for the f of x function, we would be at this point right here. So yeah,
Right.
we would be able to say limit x tends towards 0 for g of, oh, let me try again. For f of x is in fact 2, like you said,
Okay,
absolutely.
perfect. So if it didn't have a broken or like not broken, but like if it wasn't separated like that, then this whole like equation would be a function or the graph. Sorry.
Sorry, what was
So
the first part?
sorry for
No
g of
worries.
x, if it wasn't a broken line, then the whole thing would be a function and we would be able to find the limit for it.
Yes, exactly. Absolutely.
Perfect. Thank you.
Perfect.
Yep, you betcha. Other questions so far? Okay, these are really excellent questions. I appreciate them. For me, these things are really foggy because it's not just about the limit concept. We also have to be familiar with what exactly is going on with this graph with all the solid dots, the open dots, and that kind of stuff. So that's why we're going kind of slow whenever a graph problem comes up, because it really is a lot of information. It just doesn't seem like it at first until we delve in. So the related idea here for f of x is the limit exists. It would still exist if there's an open circle there, a solid dot, which is what's implied because it's graphed through. This limit exists even with the open dot there and a weird definition down below. So the only way we break the limit is if we do this. Let's bring back the original curve now. The curve went from a height all the way up to 3. Then it jumped down to a height of 1. And this is what you're looking for when the limit fails to exist. Let's make a big deal out of this section of the graph. So on that section right there, do to the break in the graph, we don't mean a break like this. That's just one point that was moved. One point does not affect a limit whatsoever. Infinitely many points being broken from the graph does matter. So when this happens, the limit lim x tends towards 0 of g of x does not exist. Or you could just say, again, DNE for short on does not exist. So watch out for these things. We're going to later call them jump discontinuities, but that's in section 2.5. For the moment, watch out for a big break in the graph, as opposed to this. This one's actually just fine. It's just 1 point moving. The limit will exist on that one. So there's a lot of tiny little details like this to consider whenever we're dealing with limits. But other questions at the moment before we try out the next? Okay, let's give this next one a try. Limit as x tends towards -1. It's a f of x times a g of x. Let's pull out our trusty limit laws. Again, this is just scrolling up in the notes. The one that would have fit that the most would be just limit law 4. Same limit law 4 that we saw in section 2.2, except we're heading towards the finite number a. In our problem, a is -1. Just says if you take the limit of a product of functions, you convert that to the product of the limit of the functions. So it's like the limit operator distributes through whether it's multiplication, addition, subtraction, or division as well on this one. So back to this diagram, we can say, forgot the limit law already. That was limit law 4 that we're using. Let's say here, so that we've said which limit law. This turns into the limit as x tends towards -1 of f of x times the limit as x tends towards -1 of g of x. And I didn't follow my own advice. I didn't look before I left. This is the leap part. So we have to double check, do either of these limits actually exist in the first place? So let's take a look at -1. We would be right over here on the original graph. That's where we have that open circle right here, or excuse me, what was I pointing towards? Sorry, that was a limit, was meant to be a limit of -1 coming out as a 1. Sorry, I think I was confusing a different question here with a different concept. The changes I made are, that should have been a -1. That should have been a height of 1. So as we head towards -1, we'd be in this location, and that does have a limit. It's the values you're getting closer to, not the function value way up here. So on this one, we'll say, this comes out as a limit of 1. Does that make sense, folks, on that first limit here? Okay, another way to see it though is if you had this printed out, maybe you're doing an exam, usually this is what I would probably do when I saw this limit. We're at -1 here, so I'd move my finger up in this direction towards -1. The values are getting closer and closer to a +1 from the left. Then I'd be looking at this area coming in towards -1 from the right. Here's where -1 is on the x-axis. Either way we look at this, function values always getting closer and closer to a value of 1, analyzing that graph. So down below, we just say it's a 1 over here. Let me erase some of this stuff so the graph doesn't get too busy. It gets harder to look at the more stuff we put on it. But that was so fun, we could just do it all over again. Now we're taking the limit of g of x as we head towards -1. So here's the multiplication. At -1, we're right over here. And the function values, whether you came in from the left or the right, looks like that one getting closer and closer to a 2 on this one. So if we're happy with the limits, we just still have to do the multiplication. But the overall result now is the limit of f of x times g of x comes out as exactly 2. This one's tricky again because of that open circle right here. This is the trickiness of that third question. Well, any questions at all, folks, on part 3 of this example? It's called example one, but it's like 6 examples rolled into one. Okay, well, we got 3 more down below. Let's give them a try next. Let me scroll to a point where we can just focus on the graph and the new limits. There we go. So 3 more limits to take a look at. Here we're dealing with a fraction. Let me zoom in just a touch. This one is a little bit different. There is 2 functions here, but the g of x function is specific. It's x squared. And here we're conflating function values with limit values, so this one is extra tricky in my opinion. Let's give them all a try. Starting with this one right here, the one with the quotient. That seems to be dealing with limit law number 5. Let me zoom just a bit more on that one. If you have the limit of f of x divided by g of x, you just take the quotient of those limits. The limit of as x tends towards a of f of x, divided by the limit as x tends towards a of g of x. But that gets us to the age-old problem in arithmetic. We still cannot divide by 0, even in this situation. So this limit law only works if the limit as you headed towards that value wasn't 0 in the first place for the bottom function g of x. So we're heading towards 3. Before we write anything at all, it's a good idea to decide, would this limit exist? Anyone see if it does or fails? Looks like some folks indicating no in class. How about in Zoom? Anyone think it does or doesn't? Looks like several people saying no in class so far. I would agree with you all. If you're doing a limit that looks like this, you immediately just want to focus on the denominator more than anything. We're heading towards 3, and so we would go towards 1, 2, 3 on the x-axis. We're right here by the red dot. So whether we head in from the left-hand side, we drop down to 0, or if we came in from the right-hand side, we're increasing towards 0. Either way, the limit of the function, the denominator, is 0. So we just say the whole thing does not exist. We need to give an explanation, so we'll just say since the limit as x tends towards 3 of g of x is 0. So this is a nice connected curve. Notice that doing the limit on this one is just grabbing the point, getting the 0 out. So that's 1 down. And, well, we kind of did use a limit law, even though this didn't exist. This was limit law 5. So next, limit x tends towards 2 of this more confusing function. We're still using the graph f of x, but the x squared is a whole new graph. So we want to analyze this one as, let's see here. Looks like this one should be limit law 4. We have a function multiplying another function, and we can break up the limit in that kind of way. So on this one, this would turn into limit x tends towards 2 of x squared, multiply the limit as x tends towards 2 of f of x. But again, this feels fundamentally different after a bit, right? That limit right there has no graph associated with it. We could produce a graph, but turns out we actually don't have to, because we can use an even different limit law here. First, I guess we should say we've already used limit law 4. Let me say that here, just so I don't forget. Okay, with limit law 4 down on paper, if we want to handle this limit, there's something that will also help us out. Scroll down to this one right here, the one we were looking at earlier. This one is a property of direct substitution in the sense that, let me grab another tool here. We're taking the value of a, directly substituting it in for x, coming out with a power of n instead of x power of n. We're going to do that right here. We're just literally taking the value of 2, dropping in place of x, and so we'll have a 2 squared once we use that limit law 9 right there. So that's the pattern of attack. Oh, hang on. There we go. Any questions so far before we write it out? Okay, so next step. We'll say by, oh geez, I keep forgetting these limit laws. This is limit law number 9. Again, you don't have to memorize what the order is here. This is more for us learning where these things are in the notes. So limit law 9. This first limit statement here becomes 2 to the power 2. So where we have the x, we're just plugging in the 2 right in that location. Later on, we'll call that direct substitution. Here, we're just reading this one off of the graph. Limit as x tends towards 2 means we're around this region. There's an open circle, but that's okay when it comes to limits. Anyone see what the value should be for this one? Absolutely. We're getting closer and closer to -1, as you said, as the x value gets closer and closer to the +2. We never actually hit -1 whatsoever on this graph, but that's okay because the value of the limit doesn't actually depend on this point right here above the red dot whatsoever. One single point can't influence the limit, in other words. So this one is just a -1. That means we have -4 altogether once we crank this arithmetic out. 2 by 2 for 4 times -1. So yeah, this one looks a lot more nasty, but once we see which limit law helps us out, not so bad, just direct substitution. I'm sorry for missing that, Parker, but exactly, we have a -1 for that limit there. Well, one more to go, folks. This time, this is the more confusing one because we're mixing operations. And just like before, even though there's no limit on that, if f of -1 is undefined, the whole thing does not exist, or you could just say the whole thing is undefined. But I think the better way to think about this one is we're just reminding ourselves how function values are fundamentally different than limit values. This says f of -1, so we will go directly to -1. We're here and grab a function value. Anyone see which value we should output? Is it a 1 or a 3? Definitely kind of tricky, right? Here's how I would probably read this graph. Oh, we got a chat come through. Yeah, that would absolutely be, or hang on, let me take another look at that. Turns out it wouldn't be 1, but good call on that. We would be passing through this coordinate until we actually hit the point right here. Again, like we were mentioning before, that's kind of what makes these problems a little bit tricky. You have to get used to dealing with the graph at the same time we're trying to understand function values versus limiting values. So on this one, we would go, when it says -1 for the function value, we go right here. Then we just move vertically, either up or down until we hit the graph. Open circle is just saying that's not actually a point on the graph. The real point is defined way up here, so we get the function value of 3 on this one to correspond to f -1. Yeah, that's very tricky in my opinion. But then we go across and do plus. This one doesn't have a limit law. This is just an ordinary limit we're doing. The way to read off this one is, let me undo that highlighting. If it says x is tending towards -1, then you're in this region. Even if there's an open circle here, it's not going to affect the limit. But at -1, this is getting closer and closer to a height of 2. If you put in -1, you get exactly 2 on this graph. So we have a value 2 here from the g of x function, which means altogether f at -1 plus the limit as of g of x as we tend towards -1 comes out as just a 5. That's pretty tricky to get through all of those. And this would be a good problem to come back to and just to revisit and see if you can get through them all once again. Well, any questions at all, folks, on getting through this problem here?
You didn't have that solid dot on the y equals fx, it would just be does not exist.
Yeah, absolutely. Let's put that in just as a separate version. So let's say our graph actually looked like this. That point's just gone, completely deleted, looks kind of fishy. But if it looks like this for your graph, let's make this just a whole new problem. Let's call this extra example. in this setup right here, if we try to take f of -1 plus the limit as x tends towards -1 of g of x, just like you said, we have a big problem here on the function value. We would say this does not exist because f of -1, again, you could say does not exist, but does not exist is usually the context of a limit. If a function value fails, we usually say undefined. If you mix the two, everyone will know what you're talking about, so there's no harm there. But this would be undefined. Only because as you take the -1 value, you go here on the x-axis, but it doesn't matter what direction you go vertically, there is no function value on this graph whatsoever. So that's what's giving us undefined. That means the whole expression does not exist. Well, any questions, folks, with this one here? Okay, well, we've done lots of limits so far, and you've probably noticed we've done a lot of limits just by analyzing graphs. That means when we come and do an exam 1, I take a careful look at what we really did in our lecture notes, what we did in WebAssign. We'll have a lot of graphs as well on our first exam, just to match up the content that we've actually been doing in class. But this is at the point so far in section 2.4 where we're doing problems similar to these. Let's pause for just a moment. Way back, it already feels like a while ago, in section 2.2, we were also doing limit laws. Here are those old limit laws, pretty much the same kind of things you're looking at before. Even say limit law 6 has the same condition here. But we eventually started doing these sort of problems. We did the limits algebraically. There'll be problems like this on the exam, maybe not as many since we haven't done as many. But notice the different strategies. If you're heading towards infinity, our strategy was go exclusively to the denominator, divide all terms by the highest order term in the denominator, x cubed. Anytime we have something at a 1 over x to any positive power, we got a 0 out. But in our section, we have to change all this up because we're heading towards finite values. So these limits start to go very fundamentally different from what you did in section 2.2. To me, that's the hardest thing about exam 1. We have to separate our minds the difference of x tending towards infinity versus, say, x tending towards 0. But before we get to all those, let's begin by putting this down on a clean first page and start with our direct substitution properties. This is a bit of a preview, but this is literally the next section, so this is a good time to mention it. Anytime I say direct substitution property, that's just a way to say a property of continuity. We'll have lots to say about continuity in section 2.5, but by continuity, we mean you graphed your curve without ever lifting up your pen, putting in a hole in it, without ever letting your curve jump a whole bunch up or down like we've seen before. You just have a nice, smooth, clean curve like that. So that's what we mean by continuous. The moment your curve does this, that would be a discontinuous curve because of that big jump right here. So direct substitution properties work really great if the graph of your function has no holes, breaks, jumps, vertical asymptotes, and other weird things that can happen. And it's really just doing what we did earlier with limit x tends towards 2 of x squared. All we did was this. We took the value a, plugged it into the function. Up here, it would look like this. We just take the value 2, plug it up into the function. This doesn't work for every single function, but the first class of functions we want to discuss that are continuous, they have a property of direct substitution, are the polynomials and the rational functions. So these are going to be the world's all-time easiest limits to evaluate, so long as the value you're heading towards, a, is actually in the domain of f. This is where the biggest problems come up. And that's why this section is a little bit longer. There's a lot of different algebraic techniques we have to come up with whenever a domain issue comes up. So we discussed remark 1. Direct substitution is really just a property of continuity. And remark number 2 is If we're going to use this property, we need to know what are the polynomial functions, what are the rational functions. So example 2 is just meant to be kind of a relaxing review. Write down some examples of polynomials, some examples of rationals. Any questions, folks, before we exhibit some of those examples? Okay, let's start with the polynomial functions. Polynomials can be defined in lots of different ways, but I think it's easier for us right now just to define polynomials through a series of examples. So if f of x equals 3x squared plus 6x minus 8, we've got a valid polynomial function, and this has degree 2, due to this power 2 right here being the highest order power. If we write g of x equals, let's say, 7x minus 8, this is also a polynomial function. Sure, we would call this one linear. We sometimes call the one above quadratic, but they're all under the class of a true polynomial function. And this one has degree 1, just because right here you're dealing with x power 1. If you write down something even weirder, like h of x equals 3, it's just a constant function, but that's considered a degree 0 polynomial as well. So all of these would be considered ordinary polynomial functions. These are functions for which you can take the limit pretty much immediately. Let's do one just for the sake of while we're looking at this concept. Let's suppose, just for a related example, we want to take the limit as x tends towards, let's make it be a 1, so we don't have to work too hard, of 3x squared plus 6x minus 8. So if you saw this as a random problem out of nowhere, maybe it's a quiz, exam, or WebAssign problem, the first thought you should have is, that's just a polynomial on the right, and polynomial functions have domain all real numbers. Let's say that right here. Domain is R. That R is just the set of all real numbers. We should say that specifically. All real numbers. I didn't have a space to write in all real numbers, so I used the shorthand. And if you like interval notation, the symbol R that you see written there is just a way to say negative infinity to positive infinity. So if you can use a direct substitution when A is in the domain of F, but your function f is a polynomial, that means direct substitution will always work on this no matter what. We just plug a 1 exactly where x's are. So we get 3 times 1 squared plus 6 times 1 minus 8. So that's 3 plus 6 minus 8 for a value of 1 altogether. So again, that's a wonderful limit only because we had a polynomial. Any questions, folks, with part A, dealing with the polynomial or the examples on the left? Okay, then down below, the rational functions are not as forgiving because these will have domain issues. This property fails when x is not in the domain of your rational function. And let's write down some examples of rational functions then. The rational functions could be something like f of x equals 16x squared minus 3x divided by 5x minus 4. So that would be a typical rational function. The numerator is of degree 2, denominator is of degree 1. Another rational function could be g of x equals 1 over 5x minus 4. So this in its own right would be considered rational, even if nothing special is going on in the numerator. If we really want to extend the concept, we could take a function like h of x equals 3. That in its own right is considered rational because a rational function just has to have a polynomial in the numerator. Well, the constant function 3 is a 0-degree polynomial. A rational function also has to have a polynomial in the denominator. But you can make that happen as well. Just divide by 1. So degree 0 polynomial above and below. So the concept here is ordinary integers are considered rational functions. But usually if you say rational, you're expecting something at least like this probably something like this as well, like a fully fleshed out polynomial higher than degree 0, possibly in the numerator, denominator, or both. But it still is important to know that's also a rational function in its own right. Like before, if things work out just right on these, we have a direct substitution property. So let's take the limit as x tends towards something nice. X tends towards, let's say, 1 of 16 x squared minus 3x over 5x minus 4. We scroll up for just a moment. It says we can use this as long as a is in the domain of the function. The value a in question is that value 1. We can tell if it's in the domain of the function here on the right just by plugging in 1 into the denominator. We get 5 minus 4, which is 1. That means we're in good shape. If we had a value that sends the denominator to 0, that's when we've left the domain. We have to do something harder on this problem. But on this one is in domain, so we just plug 1, once I select the right pen tool we're going for. We just plug 1 numerator and denominator everywhere x occurs. So it's 16 times 1 squared minus 3 times 1, divide by 5 times 1 minus 4. So numerator, this is just 16 minus 3 for a 13. Denominator is 5 minus 4 for a 1. Oh, darn it, and then that simplifies down to a 13. So these are two examples where things work out just right. They always work out for polynomials. There's no domain errors. But we'll see examples later on the notes. This is why the notes are a little bit longer, where this fails. For example, if we're heading towards maybe it's 4/5, that would produce a 0 in the denominator, and we would have a problem there. We can't use direct substitution, yet the limit could still exist. So we have to do something algebraically to investigate even further. But that's what we're getting into in the next topics. Think again of this sheet right here as just a surely algebra review. The calculus is on the right, written in the orange pen. The major thing is recognizing the polynomials and the rationals. Any questions, folks, with the example 2 so far? Okay, looks like we're getting closer to our 10-minute warning. We're just about out of time. And what we've got next is direct substitution property restated. Looks like we have a couple limits that we can run through. Then beyond here, we're getting towards the meat of the next section, example 3. This is where most of the problems we're going to be working out in WebAssign comes from. So we're inching towards it. Let's first take a couple more just relaxing limits before we get started. This is on example 3. Evaluate the limit, and if it does not exist, we'll explain why. First thing to observe on this one is it's a rational function, and 0 is in its domain. We know it's in the domain because if you directly substitute 0 here and here, we just get -1 in the denominator. That means, yeah, 0 is in the domain of this function. We plug in a value that gets us 0 in the denominator. Again, we're out of domain, and we have to do something else. But this problem just becomes direct substitution. We take the value 0 from the limit and plug it in. So this is 0 squared minus 2 times 0, 0 squared minus 0 minus 1. We have 0 divided by -1. Looks concerning, but this is defined. This gives us the value identically equal to 0. So this is a case where it worked out just fine. We'll see again in the notes cases where it doesn't work in example 3. Well, any questions, folks, with that one there? Okay, in a way, just kind of relaxing algebra doing these kind of limits. And to a large degree, that's what's going to happen in section 2.5. We're dealing with continuous functions. And so a lot of the limits you'll notice in section 2.5 go exactly like this. Now, next in part B, we're taking the limit as x tends towards -3 of this weird function. Doesn't look like direct substitution property works because this is not a polynomial function due to the square root. That's enough to break it. There's a polynomial function on the inside, but there's a square root function all at the same time. And it's certainly not a rational function. We expect polynomial divide by polynomial. So that alone prohibits it from being both polynomial and rational. So we need something else. So here comes a limit loss to save the day. Let's scroll through here and just find something that's relevant. I guess we're already there. At the bottom of this whole list, it says, if you take the limit as x tends towards a of the fourth root, or excuse me, the nth root of f of x, let me zoom in on that, you just get the nth root of the limit of the function. Saying the limit operator can go on the inside. But there's something new here, right? There's a 5 in front. There's no 5 in front of this one. So really we start off with this limit law. Limit law 3 says, if you have a constant times a function, the function is this square root part. The constant c is 5 in our problem. You can make the limit operator go between the constant and the function. Let's begin with limit law 3 to start off on this one. So as a paper trail, this is limit law 3. And this turns into 5 times limit x tends towards -3 of root x squared minus 2x. So limit law 3 doesn't look like it's a big deal, but you know it helps. It allows us to focus on what matters, the function, not the constant that was multiplying the function. Now next, we go down to all the way to the bottom, limit law 11, which says the limit operator in front of any root whatsoever, we have to make sure that if it's an even root, that's us. This is a square root, so that's a 2 that we usually don't write in there. The value of the limit has to be positive. So plugging in a -3 here should give us a positive value. This is the only way this property can break. So next, by limit law 11, let's indicate that here. Limit law 11, we get that this is equal to 5 times the square root of the limit x tends towards -3, x squared minus 2x. Let's take a look at our limit law, see if we've done exactly what it says we can do. So the limit operator was in front of the root. We commuted it inside the root now, and that's what's being expressed right here. So why do all that? Well, we were looking for the polynomial because we can use this direct substitution property when it comes up. And that's a polynomial finally. The limit operator wasn't concerned about the 5. It wasn't concerned about the root. We just take the limit of the polynomial and then take 5 times whatever the square root is of that value there. So now we can use direct substitution and say, scroll just a little bit. This is equal to 5 times the root of, if x is heading towards -3, direct substitution means you write in a -3 here, square it, and then write in a -3 there. Now we're just kind of following our nose with arithmetic. This is 5 times the root of, -3 squared is a 9, plus 6, becomes 5 root 15. And that's a simplified value. We wouldn't have to do anything further on that limit there. So that's how this kind of limit comes together. Whenever it's a little bit more built up, sometimes we can still just make it work. And notice, effectively, what we did right here is we just plugged -3 here and here. Direct substitution worked for this, even though the original function wasn't a polynomial. But we had to stitch it together through different properties of the limit law to all make that happen. Later on in the next section, we'll say this is a continuous function. And so it was appropriate to just plug in the values right to this step for a pretty big shortcut. Well, we did it, folks. That's a couple limits done purely algebraically, no associated graphs attached to any of these. Any questions at all seeing these done? Okay. Even though these problems didn't have a graph, for the last thought of the day, if you're doing this problem as a WebAssign problem, or maybe more critically, a quiz problem where the stakes feel a little bit higher, you might want to just double check your answer by producing the graph. That's what we're used to seeing. Let's connect what we did here purely algebraically with what the graph might say. This doesn't work for solving the problem because as an exam or quiz problem, you have to show these steps. But whenever you can give a good check on a problem like this, you might as well take a advantage of these sort of tools. So let's plot f of x equals 5, SQRT produces the root, x squared minus 2x. That's an odd looking function, but notice we only care about being around -3 because that's where we're heading towards. So let's refine our domain and say -5 less x less positive, or let's go -1, something like that. We do that, this is our graph. So nearby -3, this is all we care about right here. We set our value as 5 root 15, so we just should plug that in. 5 square root 15, close to 20, about 19.4-ish. Let's zoom in here. And now this is what the check would look like. You're always looking to that spot in the limit statement. It tells you you want to take your values to get closer and closer towards the -3. So watch that first coordinate. As I inch towards -3, I should be getting closer and closer to about 19.36. And yeah, sure enough, I'm getting really close to -3 at this stage. It looks like the closer you make it, well, I landed right on -3. The closer you make it, the closer the function values match up. It doesn't matter if we start from above. So here's up towards the left, -3.32. We're way out here. Function values are dropping down towards that 19 value as it gets closer and closer to the -3. So again, this is a pretty powerful tool. It doesn't work for us in an exam setting, but again, when you're learning this, take advantage of anything extra that helps connect the new stuff, doing this algebraically with what we did before, the graphs. Well, any last questions or comments, folks, with where we got to so far? Okay, I don't want to go too much further in the notes because we have some technical concepts we want to take a look at with definition 1. This is the restatement of the limit, but we're going to connect that through this really big, powerful theorem right here. This is the theorem that allows us to take a function that's not even continuous and still find a way to use direct substitution no matter what. It's kind of a tricky concept, but then once we get through this, we'll be on our last example 3, doing more similar homework problems at WebAssign. So we'll end the class here today. Any last questions at all, folks, before we call it a day officially? Yeah, go ahead.
Next Thursday, we'll have the rule laws available. So, yeah.
I was thinking of posting the limit laws. You mean for the exam 1 right here? Oh, you mean the brand new quiz,
Yeah.
quiz number 2? Yeah, that one's going to be using the limit laws. Yes.
So we'll have those available to look at.
Yeah, absolutely. Other questions so far? Okay, well, have a great afternoon, folks. We'll be right back here when we come back on Thursday's class.